This video looks at the characteristics of polynomial functions. So we'll start by looking at what are polynomial functions. So polynomial functions are some of the functions you've seen before. So we've looked at linear functions in the past, just the parent function being y equals x. We've looked at quadratic functions, y equals x squared. This one here will be a new one, y equals x cubed. But you can see the pattern here. We've got these variables to some exponents. We could keep going, y equals x to the 4 and so on. Those are all examples of polynomial functions, and we're just going to look at these three for now and talk about some of their characteristics. So here's an example of a linear function. It's a line, it has a slope that's negative, it slopes down. So the shape is a line. For the quadratic function, the shape is a parabola. It has the ability, a parabola can open up or it can open down. And a cubic function looks kind of like this. It can be kind of n-shaped. Sometimes the n shape will be more exaggerated than other times. And you'll notice here that it has two turning points. So 2 points where it changes directions, whereas the parabola just had one turning point. And if we were to kind of keep going and look at the y equals x to the 4, we'd see that it could have 3 turning points and so on. All right, let's look at the characteristics of these functions because that's what we're really interested in here. So the domain of this line and the domain of any line really is just that x is an element of the reals. So x is an element of the real numbers. X can be anything. It could be a small number, it could be a big number, it could be a negative number, it could be a fraction, a decimal, it doesn't matter. X can be anything. And again, I should probably draw some arrows here just to indicate that these functions continue on forever. Now the parabola, again, we can choose any value for x. We can choose 0, we can choose 5, we can choose 10, 12, and because the parabola goes on forever, we see here that x is an element of the reals. And the last one here for the domain, again, x can be any value. I can stick my pen anywhere, go down this line, and eventually I'll hit that function. So we say that x is an element of the reals. And that's true for all polynomial functions, is that the domain is that x is an element of the real numbers. All right, let's look at the range. For the linear function, the line goes up forever and down forever. So, and there are no gaps or anything, so we just say that y is an element of the real numbers. The parabola a little bit different. You can see that there's a point down here where we stop decreasing and start increasing. So y is never below this value. That looks like a -9 to me. So for this particular example, we would say that the range here is that y is an element of the real numbers such that y has to be greater than or equal to -9. So anything greater than or equal to, and the reason why we know it's anything greater than or equal to, these arrows indicate that this will keep going up forever and ever. All right, and the last one here for the range. If you look here, the y values go forever in the negative direction as we move here, and they go forever in the positive direction here. So the y values can actually, and there are no holes or gaps or anything, so we just say that y is an element of the reals. There are no restrictions here. Y is an element of the reals. And then we can look at the maximum or minimum values. So any straight line will not have a maximum or minimum. So this will always be the case that there are no max or min values, so there are none there. The max or min value, we'll say it's right here, and that looks like it's at x equals 1, 2, 3. Let me back up, sorry. That's at x equals 2. And y equals -9 by the looks of it. So this function would have a minimum. I'll just indicate that it's a minimum rather than a maximum. And that minimum happens when x equals 2 and y equals -9. And then we can move on to the cubic function. It actually, notice it has both a maximum and a minimum. We're going to have to estimate here. It looks like that the maximum right up in here. So we'll just, we'll say that it looks like it has a maximum when x is equal to about -1/2. So going half a unit to the right, sorry, to the left, not to the right, to the left. And it looks like we've gone up maybe a little bit more than half a unit, maybe 3/4, maybe 2/3. And again, we're just kind of estimating here. With some graphing technology, we could probably figure out exactly what that is, but just to estimate. So this is our max right here, that highest point that this function reaches. Now this is what we would call a local maximum. Notice the function. So some of you might be wondering, well, doesn't this function go on forever? So does it not have a max? I'm just going to stipulate here. This is a local maximum. It happens, it's sort of a bump, it's a turning point. We hit this sort of peak here. In this little location, we hit a peak. The function overall does not have a maximum and does not have a minimum, but it does have what we call a local max. And it also has a local minimum. Let's fix that up. And again, we can just estimate the points for that local minimum right in here. Try to read off those values. Maybe we'll just label it so we can see it. And I think I'll just add the word local here. So this is a local minimum, and this was a local max. And it looks like x is a little bit bigger than 1. So maybe 1, what is that, 1 1/4 maybe, 1.25. Or we can say 5/4 if we wanted to. And the y value looks like it's going to be -2. So you can see some of the characteristics of polynomial functions. We're going to look at a couple more. So we'll just flip to the next slide. And we're going to talk about what we call end behavior. So here's a graph of a parabola. When we talk about the end behavior, what we're really looking at is what happens to the y values as x gets really big or as x gets really small. In other words, what's happening, maybe just change the color on that so it doesn't blend in. What's happening over here and what's happening over here. And there are two ways to describe that. I mean, we need to describe each of those behaviors. And the way that we do this is we describe it as x approaches -infinity. So this little arrow here just is red, approaches. So as x approaches -infinity, so here, don't forget, this is the x-axis, this is the y-axis. As x is going this way, what's happening to the y values? Well, the y values are continuing to go this way. So as x approaches infinity, we say that as x approaches -infinity, this is the negative side, right? We've got -1, -2, and so on. So as x approaches -infinity, y is approaching +infinity. The y values are going up forever. So as x approaches -infinity, what's happening to the y values? Well, they're indicated by the arrow here. They're continuing to go up. So that's part of the end behavior. And the second part of the end behavior is what happens as x approaches +infinity. You can write a plus sign in there if you want to, but you certainly do not have to. So as x approaches +infinity, that's out here. What's happening to the y values? Well, these values are continuing to go up. So they're approaching +infinity as well. So we can say y approaches +infinity. So that's probably a new concept for you. A little bit tricky. Why don't we have a look at one? You can try it. Maybe pause the video, give it a shot, and then you can come back. So take a minute, pause the video, and describe the characteristics of this function here, and then you can come back. All right, hopefully you've had a chance to give this a try. We can see that this function goes on forever here, forever here. There are no holes or gaps. So when we talk about the domain, this is a cubic function. Looks a little bit different from the one on the previous slide. But here the domain is that x can be any number. X can be this number, it can be this number, it can be this one, the one way out here, it doesn't matter, x can be any value. And the y values do the same sort of thing. They go on forever in the positive direction, forever in the negative direction. So we just say that y is an element of the reals. X-intercepts, where the graph crosses the x-axis, That looks like it's going to be right around here. So we'll get both an x and a y-intercept. So the x-intercept is just at 0, 0. And the y-intercept is in the same location, right at the origin. All right, now let's describe the end behavior. So the end behavior are these two points, or these two locations here. So as x approaches negative infinity, that's in this direction. As x goes this way, what's happening to y? So as x approaches negative infinity, we want to know what's y approaching. Y is approaching, well, if you look here, as I move further and further this way, this graph is moving further and further this way. So it's becoming more negative. So the y values are going to get closer and closer to negative infinity. And then the last little bit, what happens as x goes towards positive infinity? So again, as x gets infinitely large, we keep moving to the right. What's going to happen to the y values? Well, you can see that this arrow indicates that we're headed in the upwards direction. So y is going to approach positive infinity. So there's our introduction to polynomial functions. Again, you've kind of looked at linear and quadratic before, but we're just adding a little bit of terminology and sort of expanding our definition of this class of functions.